Okay, so now that we've seen how to define double as an instance of map, the idea is that like other algorithms like raiseBy will also be an instance of the same pattern. And so rather than having to define them by hand, we'll be able to get them as an instance of map. Okay, so here's the idea. When we have raiseBy, we want to now think of that as coming from map. So let's define raiseBy again. The idea is that we can like replace the definition of raiseBy with a use of map on L. So the idea should be that, well, what does raiseBy do? It goes through and it adds C to every element of the list. And what does map do? It goes through and it does F to every element of the list and makes you a new list where you've done that. So it collects up the F of every element of the list. So what we want to do here is put the function that adds C to its input. Okay, so the thing that's a little bit trickier here than when we're doing raiseBy is we don't have a name yet for the function that adds C to its input. So we could make that by doing a let, and then we could say let fun add C of x colon int be x plus C in map of add C on L like that. So now if I load that and then I do my raiseBy of, I forget what the example is, 11, 15, 20 by 10, then we get 21, 25, 30, which is what we said we were supposed to get. Okay, so there's something a little bit new here, which is that we're saying let fun add C. So we haven't previously put fun declarations like that inside of a let, but you're perfectly welcome to do that, just like you can put val declarations inside of a let, you can do that. The reason that we have to do that here, whereas we didn't have to do that in previous bits of code, is that if instead you tried to put this out at the front like that, then you get an error unbound variable or constructor C because you're referring to the C here, right? Like we're trying to refer to the C that we want to add, right? I want to add, in this example, $10 to everyone's salary. Well, we're referring to the C before the C exists because the C is an input to the raiseBy function here. So what we have to do in this case is move add C into there like that. Okay, and so if we do that, then we're doing that. And so there's something a little bit new that's going on here, which is that we're kind of making up the add C function on the fly for every number C. So if, for example, you try to step raiseBy with the list 11, 15, 20 with 10, then somehow that steps to map of add C on that, which, should then be something like add C of 11 cons map of add C on the 15 and 20, where somehow we want to know that that particular add C, when we do add C of 11, is adding the C that was here, the 10, rather than adding like, something else, right? So this instance of add C somehow has to remember the 10 in some way, because that particular add C is the one generated by the function declaration here that refers to that C. So there's a way to make this a little bit clearer and explain what's going on here, which is to introduce an idea that we'll call anonymous functions. Okay, so what's an anonymous function? It's a function that doesn't necessarily have a name. Okay, so the notation for an anonymous function is the word fn and then x and then the body. And the idea is that this is like saying fun, I don't know what to call it, f of x equals body, except instead of having a name for it like f, there's no name, like f. Okay, so this is like literally writing down a function. So if I go over here and I say fun x goes to x times 2, if I say fn x, not fun, goes to x times 2, it says, hey, that's a function from ints to ints. And so how do we use it? Well, you would write something like fn x that goes to the body of the function, and then applied to 7 or something like that, right? Is like giving an input. To give it an input, you just write it next to its input like that. So if I say the function that sends x to x times 2 applied to 7, then I get 14. And so there wasn't really much reason to use this kind of thing up until this point in the course, because up until now, if we were going to write something like this, we would have just written as like, I don't know, let val x equals 7 in x times 2, and then like we're naming x7 and then referring to it in the code there. But the reason to write a function up until this point in the course was that we wrote a function because we were writing the same pattern of computation and then using that on multiple inputs, right? We wrote a bunch of functions and then we would test them on different problems, and we would have the idea that we could run the same algorithm on different problems to apply the same idea to different calculations. But here, well, if we're going to write a function with no name, then we sort of just get to use it once. If what we're doing with it is really just applying it. But really what's going to happen is we're going to write a function with no name so that we can use it as an input to map and say, here's what we're doing as input to map. So what that looks like is if I use an anonymous function, well, first of all, let's do the simple example first. I could have defined my dub_all like this. Instead of ever defining the double function and giving it a name, I could just put right here the anonymous function that sends x to x times 2, and then new dub_all of, I don't know, 1, 2, 3 gives me back 2, 4, 6. So the idea is I'm putting right here as input to map the function that sends x to x times 2. Well, that's the definition of the double function. I'm just choosing not to give it a name here as the double function, but instead to just give it directly. Okay, now what if I do raiseBy in the same kind of way? Then what I can do is to say, if I'm giving everyone a raise by C, then what I want to do is map the function that sends x as input to x plus c on L. And so this is equivalent to what we set up here, where we gave a name to the x goes to x plus c function and then plugged it in here, except instead of giving it a name, we're doing it anonymously. So if these anonymous functions are confusing to you, then you can feel free to always do this let syntax, where you just say let fun and then give it a name and do it like that. But it's a little bit slicker if you just write it inline, because then you don't have to have a whole let block. You can just write the function that you want as input right there. And so now for our new raiseBy, if we do new raiseBy on 11, 15, 20 by 10, then we get 21, same as before, right? So it's the same code as before. It's the same answer as before, but the code is different. So the point of all of this is that now we can feed functions, even functions that have no name, in as input to other functions, and use that to abstract over the different bits of two pieces of code that share a lot in common. So if we think about how new raiseBy runs, if I take my example down here and step it, then what happens is that new raiseBy on this will turn into a use of map where I send x to x plus 10 on 11, 15, 20. Okay, and so why is that? Well, when I do new raiseBy with L and C, what I do is I take L, the list I supply for L, and I plug it in here, and I take the number that I supply for C, and I plug it in here. And the fact that that C happens to occur in the body of an anonymous function doesn't change what you do at all. You still do exactly what you would have done before, which is just substitute the value that you're given for everywhere where the input occurs. But in this case, the place where the input occurs under the function. So magically, what we're mapping is a function that sends x to x plus 10. And then at that point, it's sort of easy to picture what happens, right? We get the function that sends x to x plus 10 applied to 11 at the front of map of the function that sends x to x plus 10 on the 15 and 20, which then, well, if you do send x to x plus 10 to 11, then you get 21. And then if you keep doing the recursive calls, you'll get, in the next one, the function that sends x to x plus 10 applied to 15 at the front of map that function on 20. And then, well, if you do x to x plus 10 on 15, then you get 25, and then you get that on 20. And then if you do that, you get the function that sends x to x plus 10 applied to 20 cons map of the function that sends x to x plus 10 on the empty list. And then, well, do x plus 10 to 20, you get 30. Do map of something on the empty list, you get empty list. And now we've calculated our 21, 25, 30. Okay, so nothing new happening except for the fact that when we do this raiseBy, whatever we're plugging in for C gets plugged into for C in the body of the function. So if I had instead said that I want to give everyone a raise by $100, then when I substitute that in, instead I would be plugging in 100 for the c that's here. And so I would get x plus 100 instead of x plus 10. And then if I do that, then I would go through and add 100 to everything in the list. Okay, so sometimes people use the word closure for something like this, like fnx goes to x plus 10, or fnx goes to x plus 100, because it's an example of what we might call dynamically generated code. That is, it's code that shows up in running the program that didn't show up in the source of the program itself, right? So like nowhere in the code for like the program did I particularly write the x plus 10 program or the x plus 100 function, but somehow those show up by reducing new raiseBy where I've chosen C to be something specific. So we'll say that like this function is fnx goes to x plus c, closing around taking C to be 10 or taking C to be 100 in each case. Okay, so that's the idea of anonymous functions. And there's really no reason to, ever use them. If you're confused by them, you can always do this style instead, where you write a function in a let that's inside of the variable that you want to appear in the function you pass as input. And then in the let, you give a name to the add C function for that, where you'd say x goes to x plus c, and then you could do map on that name instead. But if you get used to it, then it's shorter to write this kind of thing here. Okay, so just to wrap up, before we move on to the next example, right? So like just in case, what's on the screen is getting a little confusing here. The whole point of all of this, let me just make a new file just so I can delete everything that we've done so far for the most part. The whole point of all of this is that now, if I was writing go back and think about doing this from scratch. If I was writing double and I was writing raiseBy and I'm doing them, like if I ran into these programming tasks knowing what I know now at this point in the lecture, rather than just knowing what I knew before the lecture, right? The whole point is that once I know map, I would never write out by hand an instance of map by recursion anymore. Instead, I would say, oh, I know how to write double. That's just the instance of map where I send x to x times 2. I know how to write raiseBy. That's the instance of map where I send x to x plus c, right? Like once you start to learn these patterns of computation that are captured by higher order functions, you don't write out the instances of the pattern anymore by laboriously doing the recursion, case L, blah, 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 blah. Instead, you just know the pattern, and then you think, oh, the thing that I want to do here is do something to each thing in the list and compute the list of the results of doing that. And the way that I do that is by plugging it. Well, that pattern of computation is called map, and so I can just plug in a particular function as input to map, and then having plugged that in, then I get the code that I would have written out by hand, except I don't have to write it out by hand and, do it the hard way. And there's a couple of different advantages to not having to do it the hard way. One is that your code is shorter, right? Like map of fnx goes to x times 2 is a lot shorter than what we had for double at the beginning of the class. Another advantage to not doing it by hand is that you have fewer opportunities to make bugs, because you don't have to write the same piece of code over and over and over again. And the last thing that's important is that when you're reading code, it's really hard to read the same piece of code over and over again with minor differences. So like, I mean, your eyes kind of glaze over, you like expect it to be right. You like can't really process all the similar stuff over and over again, reading it, trying to read it in detail. And so if you do things like this by instantiating a pattern, then it's not just shorter, but you're communicating to the reader that, oh, if you understand this pattern of map, then what I'm doing here is really just instantiating that pattern that you already understand. I'm not like doing something new that you have to work to understand. I'm just deploying this thing that you already understand. If instead you copy and paste the code for map, then people are going to be like, oh yeah, that looks like a map to me, and not read it closely. And then the one time in 1,000 when it's actually something different than just doing like map, they're not going to catch that it's doing something different because they're not going to be able to read it closely enough, pay attention enough to see that it's doing something different. So there's really an advantage for reading code to writing things in terms of here's a pattern of computation instantiated in a specific way, rather than copying and pasting the pattern of computation. So a lot of the point of higher order functions or functions as inputs, functions as arguments, is that we can abstract the pattern of computation given a name, and then when we want to use it, we just say, okay, here's the pattern of computation that I'm using. I'm referring to it by name. The name is map. And so a lot of what we're going to do over the next week or so is look at different things that we saw in the first half of the semester and investigate what pattern of computation they were secretly an instance of, and then write the pattern in general, and then rewrite them as deploying that particular pattern of computation. Okay, so we're almost there. We're almost done with map. There's one other improvement that I want to make, which is that if we go back to the original piece of code, right, there was dub all that looked like this. There was raiseBy that looked like this. Both of those were going through a list and doing something to each thing in a list to get some result. Well, I could write another function that is the same kind of thing. Maybe I want to be given a list of numbers and return a list of strings. And the way I'm going to do it is if the list is empty, then empty. Otherwise, if I got x times x's, then I'm going to turn the first number into a string and then show all of x's. So for example, if I give myself 1, 4, 3 as input, then I get the list with strings 1, 4, 3 as output. So the problem with this, like morally what should happen is that we should be able to define show all as, well, what am I doing to each thing in the list? I'm doing int to string to it, like that. But if I try to load this, then I get an error because it says map was supposed to take an int to int in an int list, and you gave it an int to string in an int list. And so the problem with this is that morally this is like an instance of the same pattern of computation, right? Like this code looks exactly the same as double. It goes through and does something to each thing in the list. The only difference is that here we've got double and here we've got int to string. But the way we defined map up here was a little bit too specific because we said it takes an int to an int and an int list and returns an int list. And in this case, what we want is it takes an int to a string and an int list and returns a string list. And so I could perfectly well make that change, and then my show all would be fine. But now my double and my raiseBy don't work anymore. So if you remember back to the Tuesday before the midterm, then we talked about something called polymorphism. And the idea was that a function that works the same for all types. Right, so for example, we had the idea that, like, for example, if I'm smushing two lists, L and L1 and L2 together into a list of numbers, then it doesn't really matter what's in the list of numbers, what's in the list, right? If you give me two lists of numbers, I can smush them together into a new list. If you give me two lists of strings, I can smush them together into a new list, right? So it works for any type. So we want to do the same kind of thing to map and say we can make it polymorphic. And so the general version is going to be that if you give me a function that takes A's to B's and an A list, then map gives you back a B list, because if you think about it, what map does is it goes through L and it does F to each thing in L. Well, if L is a list of A's and F takes an A's input, then that makes sense. And map collects up the results of doing F to each thing in L, right? It conses F of the first thing onto map F of everybody else. And so if I, collect up the results of F and F produces a B each time that you run it, then the result is a list of B's. So if I do this version, then everything loads and I can do my new show all on 132 and get the list of strings, while at the same time I can do my double on 132 and get my 264. So the point is that by making map polymorphic, that is, making it work on many different types at once, but it's the same piece of code, right? So it's really doing the same thing, but for different types, just by observing that the same piece of code can work for any type A and B that you plug in, we get a more general expression of this pattern of computation. We get to say, map really takes A to B an A list and gives you B list. So in particular, right, so like, the particular instances of it that we're using are map taking F, which is an int to int, and an int list, and giving back a int list, and map giving back taking a function that takes int strings, take an int list, giving back a string list, but like, you could do whatever you want. Like, so if F takes an int list to a string list, then this would be an int list list, and this would be a string list as output, right? So you can kind of plug in any types you want for A and B, and map will go through the list and apply F to each element. Okay, so what we're going to do next is to look at another example of a higher order function, another example of a pattern of computation.